So before we start with questions, I'll go through a little more of the logistics of the exam. So it'll look very similar to these practice exams. It'll be 20 questions, and they're all going to be multiple choice. So it'll have a very similar format. So sometimes people, I think, get, I don't know, scared of this or think this is going to be harder. So, I've done different combinations of short answer, multiple choice. The grades usually end up being almost exactly the same in terms of like the mean and the variance. Because on the short answer, if you aren't really sure, or you're more likely to get some points dinged off here and there, even if you get the answer right, because you made some mistakes along the way. Well, as in multiple choice, right? Sometimes even if you're not really sure, you can rule some answers out and take a pretty good educated guess, right? So, well, 50 minutes. So be aware of time as you're taking it. To try not to kind of waste too much time on a problem if you get stuck. I'll be giving you this exact formula sheet. It'll literally be tucked into the exam. You'll have extra paper if you want it. You can write on the exam so you can show your work. I'm not going to give partial credit, but you can work on the exam, write on it. And I think that should cover the logistics. Any questions about kind of any more of the procedural stuff about the exam until we jump into, or before we jump into content? All right, so it'll be in person Friday in this room. Are there any specific questions that anybody kind of, if you've looked at the practice exams or just questions in general about a specific type of problem, we can kind of start out with those. Otherwise, I'll kind of pick and choose probably. No questions? All right, so let me think. So I did not go through these. And actually, let me re-download this from here because I think I was working on the other section, so I edited some things. So here's practice exam B. Let's scroll down. Let's actually work off this contingency table. So first of all, this might help you a little bit if you haven't completed that Excel assignment that's due by the end of the day tomorrow. But we've got kind of this combination of whether or not someone's Republican and whether or not they want marijuana legalized, right? So I've got my two events, A complement, excuse me, B and B complement. Now I left off one of these boxes, right? So then I ask, what's the missing value for X here? So there isn't necessarily an equation for this. I could actually write one out, but we haven't really explicitly looked at it. But what did I say? How do we come up with these totals? Like, let's say I didn't give you these totals. How could I come up with them? Yeah, just adding across the row or down the columns or across the rows should reproduce these totals, right? The probability that somebody wants marijuana legalized and is Republican, plus the probability that someone wants it legalized and is not Republican. What's every single person who wants it legalized, right? So when I add those up, that should give me that total. Okay. So here, excuse me, I know that 0.15 plus X is going to be equal to 0.55. Now from here, this should be fairly simple math. I mean, we'll just subtract 0.15 from both sides. We're left with what, 0.40. So, that one should be relatively easy, right? In terms of, let me blow this up here so you can see it a little better. In terms of, we just need to know that we can add across the rows and down the columns to reproduce those totals, okay? Now, I could have also done what? I could have also said that X plus 0.1 is equal to 0.5. If I do a little bit of algebra here as well, I would end up with that same exact answer. Okay. Any questions on that one? Shouldn't be too bad. And if I was doing this on the exam, as soon as I solve for this, I would write in what that probability is just for everything moving forward. Okay. So we found X is 0.40. So now I ask, what's the probability an individual wants marijuana legalized, given that they are Republican? Right? So anytime I see this word given, and I'll try to be pretty friendly on the exam, right? I think on some of the Connect assignments, it's a little more difficult, or some of the problems we work through in class. It's not always that we use the terminology of given. You might be said, oh, the probability that somebody wants marijuana legalized, knowing that they're Republican. Well, that knowing is kind of like you're given, but on the exam, I'll use this terminology of given. Whatever you are given, that's what goes on the right-hand side of that conditional line. So given that they're Republican, what's the probability that, and I'll say that they want marijuana legalized, or LM is equal to yes. So I'm looking for a conditional probability. All right. So I've got this conditional probability. So I go to my formula sheet and I'm looking at this and I say, okay, here's a conditional probability. Here's the equation I can use. This is the idea of the multiplication rule. So I've got my conditional probability is the intersection of the two events divided by what I'm conditioning on. So if this is my A, this is my value B. So I want the probability of A and B. And then I'm going to divide by the probability of what I'm conditioning on, or the probability of B, which my B is that they're Republican. Right? Oh, not new share. Is that clear? So all I'm doing there is writing out what I'm going to look for. This is the probability I was asked for. Here's my event A, my event B. I can then use the formula sheet to write out kind of that general form of the equation in the context of my example. Now from here, we should remember that a contingency table, I can't actually find directly a conditional probability, but I can find the intersection of events and I can find the probability of events themselves. So what's the probability that someone's Republican and once marijuana legalized? Well, remember, these top four left cells all represent intersections, or this and this. So want marijuana legalized and Republican, my numerator there, 0.15, divided by the probability of the Republican. Well, that would just be, go down to that total, right? The probability of the events themselves, that's what's in the total columns. So the probability someone's Republican here, 0.5. So I get what? The answer to be 0.3. So all I did there was identify what the problem was asking for, find the formula, write it out in the context of my example, and then it's just a matter of using that table to plug in those values. Okay. Any questions on that before we keep moving here? Okay. So what's the next one? The next one's actually a little bit easier. So I asked these in a different order. I probably asked them in an order which doesn't make sense. But in 7, all I want is the probability that someone's not Republican and does not want marijuana legalized. So if I'm writing this out, all I want is the probability that someone is, I don't know, not Republican and does not want marijuana legalized. Well, if I just want the probability of an intersection, that should just be one of those top 4 left cells, right? So I go, what's the probability that they don't want marijuana legalized and they're not Republican? That should just be 0.1, right? So anytime you have a contingency table and you're asked for the probability of an intersection, that's simply going to be going up to that table and identifying the cell that would give you that intersection. One of those top 4 left cells, right? Whatever kind of the row and column headings match up to whatever your probability you're looking for, or a combination of events you're looking for. Okay. Any questions on that one? Relative, like I said, this one should be like an easier one on. Right? Just finding the intersection from the table shouldn't be too bad. I'm then going to ask one that's not on here. So what if I said, what's the probability that someone is not Republican or wants marijuana legalized? Okay. So what's the probability someone's not Republican or they do want marijuana legalized? Okay. So I want to find the union of 2 events, and I'll show you where in a second where it's at in the formula sheet. But if I think about this as my event A and my event B, we know we can rewrite the union as simply adding up the probabilities of the events themselves and then subtracting what would be double counted, which is whatever's in the intersection, right? Or whatever's in both of these events. So here, the probability of A would be the probability that they're not Republican, plus the probability of B, if they want marijuana legalized, and then subtract the intersection of the two. So not Republican, and I'm running out of room, but they want marijuana legalized. Okay. So the way I knew that was if I go here, the union of two events is the probability of each event and then subtract out that intersection, right? So that's where I was kind of grabbing that formula from my formula sheet and then just writing it out in the context of my example, right? What's my event A? What's my event B? Okay. With me up to that point? Yeah, I've seen some people nod their heads. No, this is kind of small, but I wanted to show you kind of that formula here. So from there, I go to my contingency table. Well, what's the probability someone's not Republican? So no for Republican, that probability is just 0.5. What's the probability they want marijuana legalized? 0.55. Now here, if I'd forgotten that I have to subtract the intersection, hopefully I'm reminded, because if I didn't subtract the intersection, I add these up, I'm at what? 1.05. I'm looking for a probability. It has to be somewhere between 0 and 1. Right? Even if I add up all the probabilities of every possible outcome, we know at most those add up to 1. So I shouldn't be able to see anything over 1 there. Now, none of my answers were over 1, so I can't, sorry, that was an actual problem. But if I'd given you kind of some answers there, anything was over 1, you know right away you can rule that out. You're looking for a probability. So we then have to subtract out the intersection. So the intersection of being not Republican and wanting marijuana legalized. So no to Republican, yes to wanting it legalized. That was that value X, that missing value we had found earlier, right? So here I'd be at what? That union would be about 0.65. So all I'm doing, once I write it out in the context of my example, is using this contingency table to find these different probabilities. Any questions on this? Okay. So let's see if I can get the order of the next two right from memory. I have the exam written, so this might be a good thing to know. And I asked you on both practice exams. So how do we know when events are mutually exclusive and then also independent? Right? So we'll start with the easy one. When are events mutually exclusive? What has to be true if we've got mutually exclusive events, just in general? How would you describe it like to someone who's never been in a stats class? Mutually exclusive events, how would you describe it?
They can't both happen.
They can't both happen at the same time, right? So the overlap of those two things is essentially non-existent, right? There is no overlap. They can't happen at the same time. So we would say that the intersection of these two events is what? Equal to 0. That's all we have to say for the definition of mutually exclusive. So when I go back here and I look, are they mutually exclusive events? Well, they either are, because I've got a 0 in my contingency table up there, where the intersection of the two things are. We don't have any zeros here. So automatically I know that no, they aren't mutually exclusive. The only way they're mutually exclusive is if the intersection is 0. I don't have any zeros here. Right? So, or being Republican and wanting marijuana legalized, mutually exclusive events, well, no, right? Because the intersection of the two things is what? 0.15, so it's not 0. So no, because, and here, is it because the union or the intersection is not 0? Well, because the intersection is not 0, right? It's that intersection of the two events being equal to 0 that would say, yes, they are mutually exclusive. So anytime we have the intersection be something other than 0, we would say, no, they're not mutually exclusive. And here, I guess, the events, they're not A and B, it's just being Republican and wanting marijuana legalized. So LM and R. Okay. Any questions on that? We'll do the kind of tougher one next. So the next idea is, are they independent events? Right? So there's a couple different ways we can check for whether or not they're independent events. And I went to 9, and now we're going back to 8 here if you're kind of following up with the numbers. So are they independent events? So the literal definition of independence is what we would call the conditional probability of A, right? I'm still looking for the probability of A. I've just conditioned on something else occurring. If the conditional probability of A is the same as the unconditional probability of A, right? And we're not conditioning on anything. If that equality holds, we would say these are independent events, right? Knowing that B has occurred, if it doesn't change the probability A occurs at all, then they're independent from each other. Doesn't matter if the other one, if I know the other event has occurred or not, it doesn't tell me anything about the probability of A. It hasn't changed it at all. So we can check for this in a couple different ways. So this is the literal definition. So when I go to give my response, it's either going to be yes, because the unconditional and conditional probability are equal to each other. So first of all, when I see a yes here, this one doesn't even make sense, right? Potentially, it's yes because the unconditional and the conditional probability of wanting marijuana legalized are the same. Or the answer has to be no, because the conditional probability is not equal to the unconditional probability of one of the events. Right? So right away, it's got to be either B or D, right? They either are independent because this conditional probability is equal to the unconditional probability, or they're either not independent because the conditional is not equal to the unconditional probability. Now here, I actually have to figure out whether or not they're independent, right? So how can I find this conditional probability? How can I find this unconditional probability? Well, let's write this out in the context of our example. So we've got probability of being Republican, given we want marijuana legalized. We want to see if these two things are equal to each other. Right? Well, what's the probability somebody's a Republican? That's just 0.5. So if this conditional probability is also 0.5, they're independent events. So how can I find a conditional probability? Well, we actually did this earlier. We said that was actually, that was actually going to be the intersection of these two events divided by the probability of whatever I'm conditioning on. Right? So that came from here, and we used that earlier. Right? Any questions there before we keep moving? Okay, so what's the probability someone's a Republican and wants marijuana legalized? 0.15. Excuse me, divided by the probability they want marijuana legalized. 0.55. I'm not sure what this is off the top of my head, so I'm going to cheat here. About 0.27, right? So this is approximately 0.27. That is not the same as 0.5, so the equality doesn't hold, and I would say that they're not independent events. Right? So are these two events independent? We would say no, and it's because the conditional probability of being a Republican was not the same as the unconditional probability of being a Republican. Any questions on that? So, one thing you're looking for in these independence examples is whatever's on that left side of that conditional line, that's what you're trying to find the probability of, right? So you need what's on the left side of that conditional line to match up with whatever your unconditional probability is. So like, notice in A, this is what we would call the conditional probability of R, or the conditional probability of being a Republican. Well, we're comparing that to the unconditional probability of wanting marijuana legalized. That doesn't tell us anything about whether or not they're independent or anything, right? We have to be comparing the conditional probability of R to the unconditional probability of R, right? So whatever's on the left-hand side of that conditional line should be matching up with whatever's just kind of over there on the right-hand side of that unconditional probability. So like B doesn't make any sense. The rest of them do, right? The rest of them, what's on the left-hand side, or sorry, B makes sense. A doesn't make any sense. That's the one where they don't match up. The rest of these, what's on the left-hand side of that conditional line is the same thing that's over here, kind of on that unconditional probability. Any questions over anything that we just kind of went through there? So I would know how to kind of solve all of these. I would also know how to do the union of two events. So I kind of added that additional problem in earlier, right? That would be a good thing to know, wink, wink, okay? No questions on any of the other stuff there? Okay. Let me think. We'll go through this one. Let's do number 10. So let's say we've got this kind of diagram below, and we want to know what the probability of B is. All right, so this circle is kind of event B. This white circle is event A. Kind of here's where they cross over, or the intersection. And then I would always kind of tell you what this shaded light blue area is, or the area outside of A and B, which is just going to be the intersection of the complements. So what we know is that the entire experimental outcome space is equal to 1. Right? We have a probability of 1. We look across every possible outcome. And so if I take this shaded light blue area and I add to it the area that's in these circles, well, those should add up to 1. It should fill out the entire space. So we'll kind of start out there. So I've got the probability of A complement and B complement. That's that light blue area. Oops, sorry. So the probability of A complement and B complement. I don't know why this is sticking to it. Plus, what's the area that's in either one of these circles? How would I write that? That's the probability I'm in either one of them. I could be in A, or I could be in B, right? That union, that was our or, right? I'm either in circle A or I'm in circle B. So those two areas have to add up to 1, right? Those kind of fill out my entire experimental outcome space. Well, here's where I have to use the definition of the union in order to solve this, right? So I've got A complement and B complement right here. And I'm just going to rewrite the union. So I said earlier, we can write the union as the sum of the two events, but then subtract out the intersection of those two events. So all I'm using here is the knowledge that this entire experimental outcome space is 1. So I'm going to find kind of two components that would fill out the entire space. That would be this light blue area, or the intersection of the complements, and then add to that the union of the two events. I then rewrote the union, right? And now from here, it's a matter of plugging my values in, right? So I was told the intersection of the complements is what? 0.2. I've got the probability of A is 0.5. I'm looking for the probability of B, so that's what I don't know. And then the intersection of these two things, A and B, was 0.1. And those should all add up to 1, right? And now it's just a little bit of algebra, right? So I've got what? 0.7 minus 0.1. So subtract 0.6 from both sides. So if I add these up, I get what? 0.6 plus the probability of B, subtract 0.6 from both sides. And I'm left with the probability of B should be 0.4. So once I had that written out, I've got one equation, one unknown. Now it's just a little bit of algebra. Okay. Any questions on that one? Yeah.
Could we also like make the grid together?
Yeah, if you wanted to do that. And I think this is some of the Connect homeworks. I think I told someone to do that because it makes a little more sense. So you could create your contingency table, right? So I think that, if I'm looking at this contingency table, I've got the intersection of the complements is 0.2. I've got the intersection of the two events is 0.1. The probability of A, that would be my total column, is what? 0.5. So here, if I try to do that, well, I can't actually do this, but I would think it's probably harder, but you could do it this way, right? So if I know that the probability of A is 0.5, what does the probability of A complement have to be? Yeah, right? These totals, when I add across or down, should add up to 1. So now that I know that the probability of A complement is 0.5, how could I fill in this missing value? Well, these two things should add up to 0.5. So this should be 0.3. Now I can head down the column to get the totals down here. The probability of B is 0.4. Yep. So you can do it that way as well. You just really there, you'd have to remember that if I probably have an event and its complement, that would have to add up to 1. So if I know 1, I automatically know the other. Yep. Any questions on that one? Yeah, whichever way is easiest for you to think of. I think this is probably a better visual, and it may be a little bit easier if the visuals kind of help you with some of this stuff. But either way, right, we end up with the same answer. Okay.